Light is not the same as heat. Let's note the difference, okay? So these are non-omega kind of devices you may see. We'll come to diodes later when we get to resistors and then transistors and then the other gadgets that are used in our everyday lives, okay? So this is a brief one, just something to touch on. We'll come to it later. So we'll move on to the next one. So we can look at resistivity. So let's say this is a resistor or any wire. Electrons are trying to go through it. So the electrons have masses in there. So as they are trying to pass through, they are meeting resistance, and that is what we call resistance, okay? Okay. Now you realize that resistance will be proportional to if the diameter or the radius is small, the resistance is great. Okay, so in that case, if the diameter is small, resistance is great. So resistance is what greater when diameter is what small. So that is 1 over diameter, which you can make it what R. Or let's say the cross-sectional area. The cross-sectional area A. Okay, the cross-sectional area is dependent on the radius R, right? Now we can also say that in terms of length, if it is longer, then you have more resistance. So resistance also proportional to length. So if we put this together, then resistance is proportional to L over A, and this will reduce to, we change this one to constant proportionality K L over A. This has a property of the material we call resistivity of the substance in question, the one that you are talking about. We can look at the opposite of resistance, which is what we call conductance, okay? So conductance we can represent by G. So see that G will be proportional to, instead of the bigger the diameter, the faster the conductance. So G is proportional to A, and G will be inversely proportional to what? The length, okay? So I'm trying to relate things so that you can get the picture very well. So in this case, G will be equal to what? K A over L. Right? So this should have a property of what? Conductance. Okay? This should have a property of conductance. That's what I mean. So we can get this also in mind as we work with properties. Okay. Now let's look at some small properties that you should be looking at so that we can also make use of that. So this is the resistor. This is the cell. This cell has E. This cell will have almost everything will have some resistance in it, okay? So this one actually will have some resistance. We can denote that by small r, okay? And then of course it will have some current through it, right? So this plus something, your E left, let's say E to ground, okay? This will be a component in it, will have a certain voltage, okay? For the small resistance in it will have a certain voltage, so that is it. Okay. So what I want to say is that the EMF, which is the power driving electrons in the cell, will have some resistance, the internal resistance. Okay, this is the internal resistance. Okay, so that is it. Okay, and then you have the voltage. Okay, so the voltage plus the internal resistance voltage will be equal to the EMF. Okay, this is what I want to say. Right. So this is for the cell. So this is for the cell. Okay, voltage. So voltage for the small resistance together is the EMF of the cell. Alright, so it's this one which is going to be equal to the voltage of this one. Okay, so it's going to be equal to voltage, whatever the sum or the voltages in the circuit. The sum of the voltages in the circuit, sum of the voltages in the circuit. Right, that is what I want to draw attention to. Let's look at some few formulas to derive here. Let's look at power. Power is work done. You said it's equal to force times distance. But when it comes to electricity, it is the charge times your voltage. Okay, that's work done, or energy is equal to charge times voltage. Now charge is giving us your current times your time, because current is equal to dq dt, right? instantaneous to this state. Now this would mean from here, and this going for this, W or work done is equal to Q, substituting this one in place of Q. Current times time times V. Times V. Okay? Right. So this is the work done. Now power is in general sense is taken as energy over time. So this energy, IT V over time, T. This T cancels it, and power is equal to IV. So that you can say power is equal to what? IV. When you have this, you can make substitutions from V is equal to IR. So you can make substitutions, okay? In place of V, you put IR here. So it's going to be IR, and that is going to be I squared R. Okay? You can substitute for I2. That is going to be what? If you are substituting for I, then you're going to get what? V over R here. So that's also going to be V squared over R. So there is the power, the energy consumed in a second. Okay? So over a certain period of time. So over a certain period of time, the energy that you have used can be calculated in this form. Correct. So let's say power is measured in what we call watts. Okay, it's measured in watts. Okay, so that's energy times time. You should look at it as energy in a particular time. Okay, so energy in a particular time. So the work done in a particular time is giving you the power. Okay, so 100 watts tells you the energy that you have used in a certain time. Okay, right. So that is that. So the power of certain gadgets, okay, will tell you how much energy they can consume, and that will mean when you are dealing with sharing electricity or distributing electricity portions in a bigger family house, the watts for the various gadgets can be looked at, okay, to make a better calculation, okay, of energy consumption, electricity consumption. And so that is that for now. Now let's look at what we call the Seebeck effect. Okay, it's not coming with Seebeck, but let me use Seebeck effect. Okay, so if you have this, let's say this is a hot liquid, another hot cold liquid. Then you put copper in it. This is copper. Now, Siebert's demonstration showed that if the two metal wires have different temperatures, this can set up an EMF to drive electrons through. Okay, so you can have electrons going through. So let's say if I complete the circuit with another metal, let's say iron, current will flow through this just because there's difference in terms at the ends of the two wires. For a difference in temperature, so difference in temperature generates EMF to drive current. That is what you are seeing. That is Siebert's effect. Right, so note that one. So this is what is used in thermistor. Okay, right. So the difference in temperature would also affect the conduction of electricity, or will lead to generation of electricity, and so on. So of course, the thermistor, that will be a resistance that depends on the temperature. Now, this is what we call the in 1822, that was what Seebeck discovered, okay, and that is what we call the thermocouple. So the thermocouple, okay, and of course this is a thermal electricity, or that is thermal heat generating electricity, right? Let's look at the next chapter. So thermal electricity or thermal current. So this is a thermocouple. a couple, two pairs, okay, thermoelectricity or thermocurrent is generated. So as a result of differences in temperature, this can be ice cold, and this can be very hot. So you have the current being forced current to flow through this to complete the circuit. So it's more or less like you have generated a cell or a battery, right? So this was discovered by Seebeck in 1822 from his experiment using copper and other devices. Okay, so based on this, we will move on to the next chapter, which I wouldn't spend much time on. We have already discussed the Wheatstone bridge and the potentiometer. It's also called the slide wire bridge. That's a Wheatstone bridge. So that has been discussed, so I will jump that and then we move on to the next chapter. Let's look at the next chapter. Alright, so that will bring us to the end of the direct current kind of electricity. We'll move on to magnetic field in the next chapter.